Hello, welcome to this video about the application of distributions of random variables for analyzing the failure of electronic components. This example is very interesting because we are combining information using different distributions. Consider the time of operation until failure of a certain type of electronic components. Could be resistors or condensators. I don't know if you are familiar with electronic components, but they are used for any device that you can imagine, and we use on a daily basis in our life, such as mobile phones, computers, and so on. So consider the time that these components are working well before they have some kind of failure. That's a very important question in engineering. We are measuring this time until failure in hours or of working. So we consider that this time, this variable follows an exponential distribution, as it is shown there, with a median of 69 hours. That's a data that's going to be very important for the problem. So, if a component is still working after 100 hours, what is the probability that it will continue working, it will continue to be operative in total more than 250 hours? To answer this question, first of all, you need to define the variable. And the variable, we will refer to the variable as t, which is something usual in the exponential distribution, which is quite used to represent this type of variables: time until something is broken, time until failure, survival time, and so on. So we will define the variable and we will refer to this variable as t, capital letters, probability that t is greater to 69, which is the median, is 0.5. This is the data that was given in the description of the problem, and it's going to be very useful to find the value of the parameter which is characteristic of the exponential distribution, which is the alpha, as you know. We are writing here, we are translating the information that the median of this distribution is 69 as probability that t is greater than 69 is 0.5. Why 0.5? Because it is the median. So this can be translated into the expression for the exponential distribution, PDF, the probability distribution function. It's the exponential number raised to negative alpha 69 is 0.5. And this is an equation with one variable to be found. So we can obtain the value of this variable. You just have to take logarithms at both sides of the equation, as you know. We are using the Neperian logarithm, and with this we obtain that negative 61 alpha, this is an alpha, even that the notation may be not clear, this is the alpha, is the logarithm of number 0.5. So alpha can be obtained as negative logarithm of 0.5 ratio over 69, and this is the result, the value for alpha. So this is very important because we were able to characterize the main parameter of this exponential distribution, and we would be able to obtain more and more probabilities applied to this exponential distribution. But what we are going to apply now is this property of the lack of memory. I should be familiar with this property because this is something we explained in the video about the exponential distribution. This lack of memory says, when a variable is described, or we consider that the variable follows the exponential distribution, this variable has no memory. So what does it mean? It means that the probability that something is working during, 100 hours does not depend on the number of hours that has been working before. So in this case, the probability that our electronic component works for more than 2050 hours, conditioned to the fact that it has worked properly for more than 100 hours, is not affected by this fact. we only consider that 100 hours of these 250 have already happened. So what we need to compute, as if nothing has happened before, is the probability that the variable time is greater to 150 hours. That's the property of the lack of memory, and you can only apply this property if you are dealing with exponential distributions. So to apply this formula, you can use the value of alpha we obtained before. You can see here that the alpha has been substituted as 0.01. There were some numbers that were omitted, such as 001, 005, so too many decimals. We used here for alpha 001, which is enough, and we substituted number of hours, which was 150. So the probability that the device is working for 150 hours more will be 0.22, so 22%. And what's the interpretation, the meaning of this result? We could say the probability that the device, the electronic component, is working for 150 hours is 22.2%, that's fine. But we could say also the probability that the electronic component works for more than 250 hours, knowing that it has worked properly for 100 hours, is 22.2%. And both meanings, both interpretations are fine because of the property of lack of memory. Now consider this other question. How is the duration of the device? How is the duration of the device if we consider that there is a device formed by 10 components of this type? So we are building a new device using 10 components. Each of them follow the exponential distribution. The device is assembled in a way that the first component begins to work until it fails. At that moment, the next component becomes operative automatically, and so on until the last component. At that moment, the device stops working. So we are like building a new device as the addition or working with a schema where each component can substitute other component if it gets broken. So it's a way to add information that matches with the idea of the central limit theorem. So how is the duration of the defined in that case? Compute mean and variance of this random variable. We work with time of operation of each component, which was t. We work with t1, t2, t3 until t10, which is going to be the last component. And you know that the average of each of these components is 1 over alpha. So it's 1 over 1, 0, 0, 1. It's 99 something. And it's the same than the standard deviation of the electronic components. Until this point, we are still talking about the electronic components. We apply the formulas we know of the exponential distribution to obtain mean and standard deviation of an exponential distribution. But now we talk about the device, and the total duration of the device is obtained by summing the time of 10 components. So that means central limit theorem. So we build a new variable which is t total. You can see here the variable t total, and this variable is defined as the addition of the time, working time, for each electronic component. And we will assume, of course, that they are independent. What does it mean? It means that the probability that one component gets broken does not affect the probability that the second component gets broken. And it's very important, this idea. So, according to the central limit theorem, we will consider that the average of this new variable is computed as the addition of the averages, previous expected values of independent electronic components, so 10 times 99, 55, and the variance, be careful with that because you cannot add different standard deviations. The variance of the device can be computed as the addition of variances of independent devices. So you just have to sum 10 times the variance of independent electronic components like this, and you will obtain, be careful with that, variances expressed in square hours. So usually you will need to work with standard deviation, and you will need to apply the square root to this result. And this is how you can obtain main parameters, mean and standard deviation of the device, a device that has been built adding 10 components through the application of the central limit theorem and assuming that the 10 components were independent among each other. The last question that we are going to answer in this example is, what's the probability that the device is operative less than 1,700 hours? We obtained before the main parameters of this time duration for the total device. It is something we did before, as you can see here. So now we can treat the variable as normal. We can treat the variable and make an approximation to the normal distribution. So the probability that the total time of working life is less than 1,700 will be the probability that the normal distribution close to 1,000, which was the mean, and the standard deviation 314 is less than 1,700. So you just have to compute the z-score. Remember the z-score, how we used the standardized values for the normal? As it is done here, you consider the value minus the mean, and then you divide over the standard deviation. That give us a z-score of 2.232. So if you read in tables or you check it in the calculator, that will give us or 1 minus 0.00126 or 0.98.7. So 98.7%. This is how we apply the main parameters that we obtained for the device that contains 10 components, and we are able to compute the probability to treat the variables as normal distribution using these parameters. So we computed the z-score, we went to the tables or to the calculators, and we can obtain the probability to be less than 1,700 for this device composed of 10 components. I hope that this video has been useful for you. If you have any doubt, you can go back and review any of the steps, and it is also highly recommendable that you try to solve it on your own before you listen to the response. Thank you for your attention.